Good afternoon, judges, professors, experts, and fellow participants. We're the ACE team from Taiwan, and it's our honor to be selected as one of the finalists of the 7th Mission Idea Contest. I'm Liao on behalf of ACE team, and now I will show you our work since early this year, Mission ACE, Apophis Close Encounter. As our mission title reveals, our target is the asteroid 99942 Apophis, a near-Earth asteroid named after the Egyptian god of chaos. The asteroid got its name because it had caused a short period of concern when it was discovered 17 years ago. Limited observations during that time indicated that Apophis might hit Earth with a probability of up to 2.7% in 2029. Luckily, this concern was fully eliminated soon thanks to the improving ground-based observations. Although Apophis won't hit us in 2029, it will still make a close encounter with Earth. Here we abbreviate as CE, on the day April 13, 2029. And for how close? The distance is about 36,700 plus minus 9,000 kilometers, which is 10 times closer than the Moon and almost the altitude of GEO satellites. Apophis visit is a once per 1,000-year event, and we expect that it will be a hot topic for both scientific research community and the general public in the next few years. Besides its super close approach, there are several reasons which make Apophis a perfect candidate for space missions. Apophis is a potentially hazardous asteroid, which is, by definition, the minimum orbit intersection distance less than 0.05 AU of Earth's orbit, and diameter equal or greater than 140 meters. This peculiar orbit and size of PHAs make them potentially city killers in case of a collision on Earth. For example, the Tunguska event was caused by an airburst of an object size around 200 meters, and it destroyed forests with area about 2,000 square kilometers. But the bright sides of the asteroid are that they are rich in natural resources such as metals and minerals, and they hold the key to the planetary formation. As the asteroids, they are the remnants of the formation process of the solar system. So the coming of Apophis offers an extraordinary opportunity for us to enhance our knowledge of planetary science and planetary defense. Moreover, the solar elongation of the asteroid will make the observation time of Apophis from ground-based telescope very limited from the day of the close encounter until September 2029. Therefore, in situ observations carried out by spacecraft for this extremely rare event is absolutely necessary. The primary goal of ACE is to do a physical check of Apophis before and after its 2029 close encounter because we want to know if there are any changes of the asteroid due to the tidal effect. So the mission objective will focus on the characterization of Apophis bulk properties such as the size, shape, density, the spin state, surface topography, and the regolith. We will also search for dust plumes and minimums if possible. The data of ACE can serve as comparisons to the results of ground-based observations and the physical models of the asteroid. For the payload, we think an imager and a dust detector should be able to fulfill our mission, and we choose ECAM C50 from Marine Space Science Systems and the piezo dust detector from Casper. ECAM C50 is an optical camera which is small, light, superior, and reliable off-the-shelf instrument for space imaging. It offers a relatively narrow field of view which provides us sufficient image resolution at certain separations of Apophis. As for the dust detector, PDD is a modular in situ dust and debris measuring instrument, which is also small and light. The size of detectable dust particles ranges from 1 micron to 1 millimeter at a velocity of up to 10 km per second. And we calculate the launch window and design a preliminary trajectory of ACE based on the Lambert solver. Here are some selection criteria for our best launch window. First, the spacecraft should arrive at Apophis at least several weeks before the close encounter. Second, the arrival delta V should be as low as possible. Third, the maximum time of flight should be less than 180 days, considering the limited volume for power supply and the propellant for small spacecraft. Therefore, the best launch window, as the orange box shows here, goes to the dates between July 16 to August 10, 2028. Our concept of operation goes as follows. First, ACE is scheduled to launch on August 5, 2028. After 100 days of travel, the spacecraft is expected to rendezvous with Apophis at a distance around 50 km on November 21st. Then we will make a stop to scan Apophis' entire heliosphere in a mosaic pattern to search for its minimoons. After that, ACE will slowly approach Apophis until 10 km away from it, and then hold again to take another series of mosaics. Then we will move on to the next mission stage, the pre-close encounter observation, which will be running from December 2028 to March 2029. In the pre-close encounter stage, there will be two kinds of operation modes. They are titled as global surveys. For Global Survey 1 or GS1, ACE will co-orbit with Apophis at a distance of 10 km for 55 days, which is about 5 spins of the asteroid. GS1 will operate at low phase angles, which makes the installation sufficient enough for determining the shape, spin state, and surface colors. Next, ACE will move down to the height of 2.5 km and orbit Apophis to carry out global survey for another 55 days, which is around 5 orbits with orbital velocity 1.6 cm per second. GS2 will focus on mapping topography features, so ACE will observe Apophis from all phase angles. The dust detector will be operating in GS2 because it is more likely to capture escaping dust particles at a closer distance. Note that we will practice the same observation strategies in the post-close encounter stage so that we can directly compare the observation results of GS1 to the ones of GS2. After the pre-close encounter observation is the stage of close encounter surveillance. In this stage, ACE will move back to the distance of 10 km again and stay at the surveillance position to observe Apophis for its near-Earth flyby from a safe distance and viewing geometry. The last stage of operation is the post-encounter observation. As mentioned before, the observation procedures of the close encounter will be approximately the same as the one of the pre-close encounter to ensure the images are taken under similar conditions. The entire ACE mission is expected to end in late August or early September 2029 with a lifetime of around 280 days. But it is possible to extend the mission depending on the spacecraft's condition. The ACE spacecraft is programmed with 6 operation modes: booting, propulsion, cruising, mission, communication, and safe mode. Here we consider 4 key performance parameters. First, the image signal to noise ratio should be around 100 throughout the entire observation period, and the pointing accuracy should be able to reach plus or minus 0.001 degree. Second, the desired image resolutions are 1.7 meter per pixel for GS1 and 40 centimeter per pixel for GS2. For example, the picture here from Hayabusa team shows some surface features of the asteroid Itokawa with image resolution up to 70 centimeter per pixel. If we manage to achieve these parameters, ACE will be able to tell more details of Apophis' surface. Lastly, the entire mission will take about 750 images which require 5 gigabytes of storage. The data rate shall reach 80 kilobits per second during the period of close encounter, so our data collected before then can be fully transmitted just within 4 days. As for the stage of the post-close encounter observation, the communication rate is estimated around 3 kilobits per second, which requires 70 days of data transmission time. And this diagram shows the system context of ACE. The system consists of 3 parts: the ACE spacecraft, deep space network, and data processing unit. And here is an overview and the layout of the ACE spacecraft. Our spacecraft weighs about 98 kilos with 7 subsystems on board. The ACE spacecraft will be mainly developed by TIFC, Taiwanese Institute of Planetary Science and System Engineering, with supports from several Taiwanese universities or organizations such as National Central University, National Cheng Kung University, Taiwan Space Union, and National Space Organization. The estimated cost is around $2 million for spacecraft only. Here shows our preliminary mission life cycle. So to summarize, ACE has the potential to characterize the PHA Apophis with an imager and a dust detector to address key constraints to the planetary defense and X-ray science. ACE can demonstrate a relatively low cost and short duration investigation capability for a small spacecraft. ACE can stimulate the scientific research and technological capabilities of industrial sectors in Taiwan. Thank you very much for listening, and we're happy to take comments or questions.